Hi everyone. In this video, I will explain one-dimensional linear regression. In general, linear regression is supervised learning task. Supervised learning tasks are characterized by a pair of data given to us. The first component of the pair introduces the inputs, and the second component of the pair introduces the outputs. So I will use the advantage of simplicity of this example to introduce and illustrate key concepts of the supervised machine learning task. So we start off inputting necessary libraries and also creating some auxiliary class to draw 3D arrows. Next, we will create our data. First, we create our ideal data by using linear function with slope 5 and intercept 3. This is our straight line. Next, we will generate some noise and add the noise to the original straight line. So this way we are getting noisy data, and this noisy data we will use as desired output, and the desired input will be x values for our input variable. How can we now characterize the difference or the error between the noisy yellow line and the ideal straight blue line? So for this, we can take a difference between each point, and we show it with vertical black lines for each data point. So now the question is, if we can use this error information to come up with a way how to approximate the noisy data with a straight line without knowing ideal line and its parameters. For this purpose, we will use mean squared error, which is a cost function. So cost function is a technical term. This means a method to measure the performance of machine learning model. Cost function quantifies the error between predicted and expected values and presents the error in the form of a single real number. So mean squared error fully satisfies this definition. In order to compute mean squared error, we will compute error between each value of the data. In our case, this is y noise, and the predicted value, which is the output of the linear function, which we parameterize by w multiplied by x plus intercept p. And we will do it for each data point. Now let's compute mean squared error. First, I will compute it using the for loop, just going through each data point one by one and summing and squared errors. There is, however, many other ways to do it. One of more simple and neat way of doing that is to use a dot product. So first we will define error, and we will apply the dot product to normalize it with the number of samples. As you can see, both these values match. For now, for machine learning task, we are usually given y's and x's. And our task is to estimate parameters of the approximation function. So in this case, we need to estimate w and b. So we will look at mean squared error as a function of parameter w and parameter b. So now let's draw how mean squared error looks then values of W are varied and B is fixed. And you can see this is a parabolic function. Now let's have a look how mean squared error looks like. Then B values vary and W value is fixed. No surprise, this is also a parabolic function because we have a second power of the error. And finally, let us have a look at mean squared error as a function of both parameters, W and B. For this, we will create the grids and compute the value of cost function at each point of the grid. So now let's confirm the shapes. So the shape of a cost function is 61 by 51. The shape of weights is 61. Shape of weights grid is 51 by 61. Shape of B is 51 and shape of B grid is 51 by 61. So we actually need to transpose value of J in order to be of the same size with W grid and B grid. And that's what we will do here while plotting in 3D space. So these blue wires, they illustrate how cost function looks in three-dimensional space. Then parameters W and B are from roughly -2 to 10 and from 0 to 10. Here I also explicitly depict 2 points. First point is a red point. This is a point which takes the fourth value of W parameter from the list of various values, and B value for the red point is the second value from B list for various values of parameter B. And finally, value of a cost function is a corresponding cost function value. And then the second point is green cross. This is actually the point where W equals 5 and B equals 3. So this point represents our ideal values for parameters, and therefore the value of a cost function here should be 0. So how are we going to travel from this point to the vicinity of optimal point? For this purpose, we will use a technique called gradient descent. So first we will compute the gradients with respect to parameter B and with respect to parameter W. And next, we will use some portion of this gradient in order to travel along the cost function surface and get the new point. Doing so, we expect a few things to happen. First of all, we expect values of gradients to decrease. Second, we expect that each next step will be shorter than previous one because the gradients are getting smaller. Finally, we expect value of cost function at each new point to decrease, and at the end of our journey, we hope to reach some close vicinity of the optimal point. We should never hit the ideal parameters, but we should converge to some vicinity of the optimal point. Now let's go back to our code. So in order to implement gradient descent, we will need to compute gradients. And for this purpose, we have to derive formulas for derivative of cost function with respect to parameter w and cost function with respect to parameter b. Derivative of cost function with respect to parameter w equals average of the following multiplication: 2 multiplied by x value multiplied by corresponding error value. Derivative of cost function with respect to parameter b is average of 2 multiplied by error. So now let's implement this. We will randomly initialize parameters w and b in order to have some values. Then we compute the predictions, the error, which is difference between predictions and the noisy data, gradient for parameter w, and gradient for parameter b. Next, I will draw the gradients in the 3D space. Because the values of the gradients are huge, I am taking only some portion of the gradients in order to visualize it in the 3D space. So next, we will update the parameters as follows. We will take a parameter and deduct a portion of a gradient from its old value and assign it to the new value. And we will do it for both parameters w and b. This portion of the gradient is called learning rate, and usually it's set to a small number. In this case, this is 0.01, but sometimes this learning rate can be much lower, or sometimes it can be 0.1. So it all depends on the algorithm and a particular optimization procedure. The reason to use this scaling parameter is to make gradient descent stable. If we provide a huge value of the gradient into this equation, the change of the parameter value also will be huge, which will cause, if you provide a huge value of a gradient into these equations, the change of the parameters will also be very big, and it will cause instability in the gradient descent algorithm. So now let's summarize what we have done. We have initialized parameters with random values. Then we computed predictions, error, and the gradients. And then we computed value updates for parameters. Now let's implement this algorithm fully. So first we initialize the parameters. Next, we will define some auxiliary variables to track change of parameter values in time. This will be w in time and b in time variables. dw in time and db in time are variables to store gradient values, and mse in time is variable to store various values of cost function. And we'll run this algorithm for 120 iterations. So in the first step, we'll compute cost function and gradient. So we compute the predictions, we compute the error, then we compute the gradients, and the cost function value, and then we record these values. On the second step, we define the learning rate and compute value of parameter W and of parameter B, and record these parameters into corresponding variables. So let's run this over. So after 120 iterations, parameter W is 4.93 and parameter B is 3.45 and the loss functions is 862. So now let's explore convergence of the parameters, cost functions, and gradients. So as we can see, parameter W indeed converges to its true value where W equals 5. Parameter B is oscillating and gradually converging to its true value B equals 3. The loss function is decreasing in time, and gradient of parameter W is decreasing and gradually converging to 0. And similar picture happens for gradient of parameter B. Here it decreases, then slightly increases, and then converges back to 0. This is fully expected behavior. Now let us visualize the gradient descent iteration by iteration. So here I will depict evolution of parameters W, B, and corresponding cost function value throughout gradient descent. So we started initialized point and then we gradually going down to the optimal point. In the next picture, I will show it explicitly with arrows to confirm that we're actually descending at each following step to the optimal value. And finally, let us compare the original line and approximated version of it. So here you can see that the blue line, which we originally used to construct noisy data, is almost identical to the green line, which represents our prediction. And these predictions are made using parameters optimized with the help of linear regression. So let me summarize a few takeaways. So first of all, we need to select approximation function. In this case, we select approximation as a straight line. Second, we need to define a cost function, which will be our indicator of how big the error between real data and predicted values is. And then we have to apply gradient descent in order to optimize parameters of the approximation function in the space of cost function. And we expect that at each iteration, the cost function value will reduce and the gradients of parameters will also be convergent to 0. In this particular case, we also know true values of the parameters, and we can say that convergence of parameters to value 5 in case of parameter W and value 3 in case of parameter B is what we expect to see, and this is ideal state of the approximation model. However, in general case, we don't have the luxury of having true model, and we don't know the true parameters where we should converge to. So this example shows basic concepts and the basic ideas which are used throughout the supervised machine learning algorithms. So thank you very much. Stay tuned for coming videos.